Okay, so thanks for this kind invitation, and honor to be here giving this lecture. I didn't look at who the previous speakers in this series were, which probably make me more nervous than anything else. But I'm going to tell you about some of my recent work that, I think Kedar mentioned some things that I did as a postdoc, and I think it's true that, what you start out working in as a student or a postdoc, you keep doing that for the rest of your career. That's kind of been the case with me, but, more recently, this, a lot of these things have kind of fallen into place. I think a lot of connections that have come together, and it actually also makes contact with something I did here at TIFR when I was an undergraduate. I came here for a summer as a VSRP student, and I worked on lattice gauge theories with Professor Gavai, and all of those things also will make some appearance perhaps when I give this talk. Certainly it's part of the thinking that goes into this. So my plan is somewhat ambitious today. I want to talk about these very sort of general ideas in quantum physics, I would say, quantum many-body physics, and sort of show you how it gives us a framework for understanding many problems in the theory of quantum many-body systems. And eventually, towards the end of the talk, I'll try to apply this to questions that are a lot of recent interest, to tell you that these are not just concepts or not just things that we like to understand better, but actually this increased understanding has an impact on us being able to solve problems and come up with new ideas for things that are being seen in experiment. Okay, so that's kind of the plan, but the first thing I would like to talk to you about is this whole program of trying to understand in a better and a more qualitative way what happens when you take many particles. You could think of them as being spins, the simplest kind of degrees of freedom. Spin could be either up or down quantum mechanically, but you have many of them in a solid, Avogadro number, large number of them. And how do you make sense of a system like that? Okay, how do you make sense of these quantum systems of many particles? Okay, and typically what you get is you have some ground state. These things interact with some Hamiltonian. There's a ground state, and as I've shown over here, there's a gap to the next state. These are the gapped states of matter, the simplest kind of states that you can try to describe. You have to pay a certain energy cost in order to make these excitations. So if you cool the system down to very low temperatures, when you're really just occupying the ground state, you're really probing the physics of this, this quantum mechanical system when it's very close to its ground state. Okay, and then you think about the wave function. We know in quantum mechanics you're supposed to describe reality by this quantum mechanical wave function. There are many different configurations that you can have for your spins. Each of them is going to appear in this wave function with some complex coefficient. Okay, so if you just think about the number of degrees of freedom or the number of, how much information you need to convey in order to specify the state of the system, just the number of particles itself is pretty mind-boggling. This is an exponential of that number. Okay, so there's really enormous amount of information in a quantum mechanical wave function, and if this is what we were trying to describe, it was going to be a completely hopeless task. Okay, so fortunately, most of this information is redundant. What we're really interested in is in understanding a system in some qualitative way, okay, to understand its basic defining features. And let me give you an analogy to a classical system. You have this phase diagram. This is the, you can think of this as the phase diagram of water. There's temperature and pressure, and you have these different phases. And if you're in a particular phase, let's say you're in this gas phase, you change conditions, quantitative things change, the volume of the gas, the density may change, but qualitatively everything over here is pretty similar. Okay, so that's the kind of understanding you're trying to achieve. Rather than describing in great detail every single point over here, you want to understand sort of the the collection of properties that defines, say, a gas phase and how it's distinct. Okay, so that's really the phases of matter. It's something that becomes sharp when you have many degrees of freedom, many particles. Okay, so it's an emergent property. You don't see it when you have 1 or 2 particles. It's only in the limit of large number of particles. And you can define these phases, if you want to be precise, as these regions that are separated by these lines, which are the phase transitions. Something singular happens at the phase transition. Again, there's no mistaking. For example, this boiling point, you go from liquid to gas, or you go from solid to liquid. Something singular happens at your system. You draw these lines, and you see how they're separated out. Okay, and those give you the phases of matter. Okay, and what we'd like to do is we'd like to do the same thing, but for quantum mechanical systems, really try to understand what are the different phases that are possible. Okay, so it turns out this problem is a little more subtle than it may appear at first sight, and that has to do with this expanded phase diagram over here. Look at the system in these expanded coordinates. What you notice is that this line actually ends somewhere. Okay, so in other words, you can go from the gas to the liquid without ever encountering a phase transition. Okay, so in other words, if you use this definition that we had over here, the gas and the liquid are actually in the same phase. Okay, so they may appear quantitatively to be very different. If you're at ambient pressure, the difference in density between a gas and a liquid is enormous. It's a factor of 1,000 difference between liquid, water, and vapor. But that distinction is only quantitative. Okay, you can begin to change that as you increase the pressure. Eventually, this difference in density can be made very small, and ultimately, the gas and the liquid have the same density. Okay, and that phase transition disappears, and then you can just circumvent that phase transition. Okay, so we had this nice picture before. We have these 3 phases of matter, but in this expanded diagram, we see that that's actually a fiction. Right? If you really look at it in a more qualitative perspective, there are just 2 phases of matter. Okay, the solid and this liquid gas, which is basically the same thing. Okay, now, of course, you may begin to worry that perhaps there's just one phase. Maybe you could go to very high pressures, and you could go around this line over here and come to the solid. Okay, how do you know that doesn't happen? And saying that you can't do it right now, it isn't a guarantee that tomorrow you can do that. Okay, so we'd like to have a definition, a way of thinking about this that will guarantee for us that this distinction is really solid. Okay. Okay, so let me give you an analogy where you can actually do that, which has this kind of flavor. So there's this game where you have these squares on which there are numbers. You can slide these things around. You have empty squares, so you can slide stuff around. And the question is, can you go from this configuration over here, where all the numbers are ordered, to this one, where all the numbers are also ordered, except for the last 2 are flipped around. Okay, so this is kind of the question of whether you can go from one state to another, in this phase diagram that we had. Of course, one way to do this is to just break this open and reassemble the squares, which is what you'd do if you got extremely frustrated. That's like our phase transition. Okay, so not doing that means you avoid a phase transition. Okay, so it turns out you cannot do this. This particular sequence, these 2 things cannot be connected. And the way you can prove that is you can define a quantity. I won't actually go into the details of that, but there's a quantity you can define which is either even or odd. So every set of numbers like this can be associated with either an even or an odd character. And what you can show is that these moves that you're permitted, they preserve the evenness or oddness of the character. Okay, and then you can show that these 2 have different characters. One is even, one is odd. So there's no way you can go from one to the other. So these are really, if we use our analogy, these are really different phases. Okay, so this is what we'd like to do for the case we did before. We'd like to have something like this, the parity over here, that will give us a guarantee that you cannot go from one state to another without crossing a phase transition. So for a long time, people actually thought they knew, they understood this for many body systems. And not only they thought they had these, the analog of this parity, they thought they had them all. Okay, if there was any distinction between phases, they could point to one of these things, and these are called order parameters. So the basic idea is that you get different phases of matter because you spontaneously break symmetries. Okay, for example, a liquid and a solid, to begin with, they have the same symmetry. All points in space are the same. In a liquid, that's, that still holds. If you wait long enough, point in space will have an atom or a molecule passing through. But in a solid, that's not true. Okay, the atoms sit in certain positions. The translation symmetry of space is broken. And that spontaneous breaking of symmetry can be captured by what's known as an order parameter. Okay, and that order parameter is sharply different for the solid and the liquid. So you can conclude that there's no way of going around that phase diagram for the ice to liquid water phases. And there are many other examples of that. That was sort of an example of a crystal. Ice is a crystal, but there's also magnetism. The spins of the electron align in a certain direction. They end up breaking the rotation symmetry of space. There are less obvious order parameters. For example, a superfluid. Okay, a superfluid state is also an example of a spontaneously broken symmetry. It's a little harder to pin down what the symmetry is. Okay, it's not one of these simple symmetries of, like the isotropy of space. It's sometimes called gauge symmetry. It's a little bit easier to think about the conjugate of a symmetry, which is a conserved quantity. Here, the conserved quantity is the number of particles, and you spontaneously break the symmetry that's associated with that. Okay, so, so all of these examples, even things that seem somewhat exotic, are really quite classical in the sense that they are ultimately described by some classical order parameter. Okay, so, so people think of superfluids as being very quantum mechanical. They are in a way, if you insist on thinking in terms of atoms in terms of particles, this is of course quantum mechanical. But if you give up that notion, if you think of atoms as waves, this is really a very classical system of waves. Okay, so so not only is all of these described by order parameters, the essential physics, the long distance physics of these systems, even if they are composed of quantum mechanical components, ultimately the physics is rather classical. Okay, so you may hope that you take atoms or spins, they're very quantum mechanical. You put them together, you might hope that that quantum mechanics survives in some interesting way. But often for the long distance physics, it's hard to obviously see the effect of this quantum mechanics. Okay, but that sort of changed in the 80s. We began to find examples of states of matter which are not distinguished by these sort of order parameters, which are not distinguished by spontaneous symmetry breaking. The first example of that was sort of amazing experiment that was done by von Klitzing. So he took a two-dimensional semiconductor, put on a magnetic field, and measured what's known as the Hall effect. Okay, you measure the voltage, you measure the current in a direction that's perpendicular to the voltage. Okay, and this is only non-zero because you have a magnetic field. The electrons are rotated by that, sort of deflected by the field, and you get some value. But what he found was kind of amazing was that this value, if you, this is the Hall resistance, rho xy over here, this red line, you can label it by integers. Okay, you can label it by some universal constant times some integer. Okay, and this is sort of maybe very typical of a lot of these condensed matter problems, I would say. When you first hear the problem, you kind of wonder why anyone did this. Why would anyone take a two-dimensional system, put on a very strong field, go to very low temperatures, and then measure this very strange quantity, right? It's sort of a strange thing to do, but what you find at the end of the day is something pretty amazing. And more than the question, it's really the answer that's extremely interesting. What is actually going on in this particular problem? Okay, so so another thing to sort of bear in mind is that people make these systems as clean as possible, but it's still a pretty dirty kind of material. And this is what the device looks like. It's got all these wires soldered on. But nevertheless, if you go and measure this quantity, it's accurate to 1 part in a billion. Okay, so the fundamental constants you get out of this, for all practical purposes, are the measurement is as good as the kind of measurements the accuracy you get in particle physics measurements, but all the action takes place in a device that looks like that. Okay, so clearly there's something very special going on that's giving us this extreme accuracy and giving us this very robust kind of physics. Okay, and the ingredient is, of course, topology. So let me give you a very brief kind of introduction. Hopefully there are no mathematicians over here who are going to be disappointed with this. But topology is really just a way to think about shapes, but retain the really robust, the really kind of global structure of these shapes. It kind of resembles a thought process about classifying states of matter. Okay, we don't want to know about the details. We want to know really what is the essence of these states. Okay, so so this is the customary picture. Donut and coffee cup are the same topology. You can smoothly go from one to the other, and that's all topology really cares about. Okay, so then there's this amazing theorem that Gauss wrote down, where he kind of wrote down a formula to actually calculate the topology of a surface. Okay, the topologies of surfaces are rather simple. It really has to do with how many handles your closed surface has. So a sphere has no handles, a donut has 1, this thing which I don't know what the name is has 2, and so on. And Gauss came up with this formula where you could find out the number of handles of a shape, G, simply by integrating this local quantity. Okay, this is the Gaussian curvature. It's something that an observer or maybe an ant crawling on the surface could locally measure, figure out what the Gaussian curvature was, and do this integral, and they could intuit they could figure out what the genus of the surface was. Okay, so this came about when Gauss was doing all his work on topography of, that was one of his many interests. And it was an example of where applied science fed into to basic science, and he ended up with this formula. Okay, of course, Gauss has many things named after him, many discoveries, but he himself called this his remarkable theorem. Okay, so we'll see there's something very similar that occurs for the other integers that I talked about, the integers in the quantum Hall effect. So it turns out that there's an analogy between this topology over here of surfaces and the topology we talked about before, or rather this quantized integer we talked about before. So in both cases, you're going to integrate something that is a curvature. This curvature over here is called the Berry curvature. Okay, and we'll talk a little bit more about it, but it has the same flavor. There's something local that you can define. You integrate that over a closed manifold, and you end up with this thing which is 2 pi times an integer. Okay, there are more physical ways of thinking about this. If you have this quantum Hall state, it turns out if you go to the edge, these orbits of these particles which are circling around, they kind of skip along the edge and end up giving you these propagating modes at the edge. And the number of these edge states is really just this integer n. Okay, that's another physical way of saying this. Okay, and there are more formal ways of talking about this in terms of Chern-Simons theories, so it makes many connections between physics and mathematics. So this is an example of the integer quantum Hall effect. So people went, they continued along those lines. They took these two-dimensional gases of electrons and went to higher magnetic fields and better samples and lower temperatures. The same philosophy we talked about before. And what they began to see is a much more complicated picture. So in addition to the integers we talked about before, like this integer over here, 1, you also begin to see these fractions. Okay? So the 1/3 is very prominent, 2/5, and so on and so forth. And it turns out you can understand these as well, but the physics is even more interesting in this particular case. It's not just electrons running along the edge. You have that physics too. But it turns out that the excitations in the bulk of the system, if you go deep inside this system, the correct excitations to describe the state are actually fractionally charged. For example, the 1/3 state over here has charge of 1/3, and they have fractional statistics. They're neither bosons nor fermions, somewhere in between, anyons. They have all of these very interesting kind of properties. So the thought was that with weak interactions or no interactions, you get these integers. As you put on interactions, you get these other states, these fractional quantum Hall states. Okay, and there's an even more interesting observation over here. So one thing you'll notice, or maybe you've already noticed this, all of the fractions over here, the denominators are odd integers, right? 1/3, 5th, 7th, 9th. There are many more fractions discovered. But it turns out that there's actually an even cleaner sample. So taking this to its logical conclusion, you eventually seeing a very particular state, 5/2, which is the only known state which has got an even integer denominator. Okay, and to explain that state, you need an even more interesting generalization that of statistics. We went from bosons and fermions to anyons. You get any phase when you take a pair of these particles and exchange them. You can generalize a phase to a matrix. The matrix generalization of a phase is a unitary matrix. And you have these states where when you take a pair of particles and exchange them, there's a unitary matrix applied to the ground state. Okay, so typically there are several ground states. There's some degenerate space of ground states, and when you take a pair of them and exchange them, you end up doing some operation on the set of ground states represented by a unitary matrix. Okay, so this is called non-abelian statistics. So it's statistics, but the operation that's involved is not a multiplication by a number, it's multiplication by a matrix. Okay, so things don't commute, it's sort of non-abelian. It's kind of like the transition from classical to quantum physics, but now at a different level. Okay, and so this was known as a theoretical possibility, but the amazing fact is that it's very likely this particular state is described by a non-abelian quantum Hall state. Okay, so all these very interesting things that appear when you start adding interactions, and an obvious question is, can we say something very general? Okay, what are the set of states that we can get that go beyond this simple classification in terms of classical orders to really talk about different quantum states that are distinguished in some way or the other. Okay, so the first thing is we talked about these integer quantum Hall states and then the fractional ones. We'd like to have a way to tell them apart. Okay, of course, you can use the Hall conductance, or you can say that one of them requires interactions, the other one does not. But it turns out that to really understand this properly, in fact, this is a fairly recent development, to really understand what is the set of states you can get strongly interacting systems, you really need to understand quantum entanglement. Okay, and that has really been the very useful input in trying to classify the different states of matter. Okay, so we have also found other kinds of topological phases. This is an example of a topological insulator. So this is a three-dimensional phase. You don't actually go down to 2 dimensions. This is really a bulk phase. It's insulating in the bulk. There's nothing much happening there. But you go to the surface, you get gapless states. You get, for example, this thing that looks like a Dirac dispersion that only lives on the surface. So it's metallic on the surface. It's an insulator inside the bulk. Okay, and we want to generalize things like this to strong interactions and so on. And for that, we need to understand quantum entanglement a little better. Okay, so I'll switch gears a little bit and tell you some basics of quantum entanglement as applied to many-body systems. Okay, so, but before I get to that, let me just mention there are some very interesting applications of these topological phases. One of the very nice applications is using this quantum Hall effect as a resistance standard. Okay, so if you want to define the 1 ohm for some very precise measurement, you can use the quantum Hall effect. In fact, apparently the kg, the kilogram, is now defined in terms of this quantum Hall resistance. It turns out that makes things more accurate rather than keeping this, I don't know, platinum block somewhere in Paris. This turns out to be a better way of defining the kilogram. And now, in fact, with graphene, it turns out you don't have to go down to very low temperatures to get the quantum Hall effect. So even at room temperature, you can get very good quantization of the Hall effect. And so people actually have these little devices where they can measure the Hall effect, the quantized Hall effect, and use that to calibrate their, the resistance standard. So that's been a very nice application. So there's talk of using topological insulators for spintronics. So this is a way of trying to generalize how to do logic in computers rather than using the charge, the motion of charge. It's quite wasteful in terms of the energy dissipation. You can try to use spin instead. And the fact that there's some interesting connection between spin and momentum on these topological insulator surfaces, it's been proposed to use these materials. This is still in the future. But probably the most ambitious application that's been proposed is to use these topological states for quantum computing. Okay, so one of the main problems with quantum computing is that you have contamination from the environment. The very delicate quantum coherence is destroyed by coupling to the environment, but you can have a certain enhanced degree of protection in these topological phases. Okay, they inherit certain robustness, and then that can help to protect, at least protect quantum information, maybe even do quantum information processing. So the non-abelian states I talked about, where you exchange particles and apply a unitary matrix, could ultimately be the logical gates of some quantum computer. Okay, so that's again in the future, but people are actually taking it quite seriously right now. Some people even think they're taking it too seriously, but there are a lot of companies investing in it. And maybe that momentum will actually, things will actually happen because of that. Actually, maybe I will skip the next part for a just in the interest of time, let me just skip to this slide on quantum entanglement. Okay, so what is quantum entanglement? So we all know that the essential ingredient in quantum mechanics is superposition. Okay, so if you had this qubit of a quantum computer that I talked about before, you can add the 0 and the 1 in a superposition. You can get this state, and 50% of the time you'll get one or the other. But really the essential feature of quantum mechanics is not so much this superposition, but really quantum entanglement. Okay, so you have not one, let's say, but two of these qubits, and you prepare this particular state where both of them are in 0 and a superposition where both of them are in 1. Okay, so this state may look at first sight very similar to the previous one. Let's say I ask what is the probability that I get a 0 on the first qubit. That's 50-50. So it kind of has the same character as the first state. But it has a different property that's very unusual, which is if you measure one of these qubits, you measure this to be, let's say, a 0, you know for sure that the other one is also a 0. Okay, or if you measure this to be 1, you know for sure that this is also 1. Okay, so this is really the entanglement of these two particles, and it was thought to be very, very strange according to this EPR paper. The main point they try to make is that the state of this system is completely known, right? When you measure this particle, the state is completely known. So a physical theory that's complete should be able to make a prediction about a variable that's completely known. And of course, quantum mechanics does not. So they try to say there's something unsatisfactory about quantum mechanics. Okay, but now actually what we know is that not only is these things possible, there are some very strange effects that you can get, which have been tested experimentally. Okay, so this feature that you have one system A that when you measure it, you find a property and you get exactly the same property in system B. It's quite easy to fake that. Okay, so you could imagine the following experiment. There are these pairs of socks, and you take a pair of the same color and make one go to one side and the other go to the other side. And then you measure this one and you find a red sock and you say, hey, I know this one is going to be red too. Okay, is that quantum entanglement? Of course not, right? That's sort of a trivial explanation. And theories like this go under the name of hidden variable theories. So you may wonder, maybe this is really all that's going on in the CPR experiment. We don't actually know what the color is. We're ignorant of that. But one of those colors is going to one side, the same one is going to the other, and then you find this perfect correlation. Okay, but it turns out there's a way to check if this is really what's going on, or if it's really something quantum mechanical, and that goes under the name of this Bell inequality. Okay, so you make not just this one measurement, but you make three measurements, three different measurements on these things, and one after another, and then you produce this combination of the results. And what you find is that there are certain inequalities that have to be obeyed if reality is really of this kind. If reality is just some fixed property that was being correlated, the result of this experiment has to lie between the two dashed lines. Okay, experimentally, what you find is these points. Some of them do lie within these two lines, but others violate this inequality. Okay, depending on this particular angle that you pick, they violate this inequality, and this line over here is the prediction from quantum mechanics. Okay, so really this violation of the classical inequality is expected, and the experiment really verifies that. Okay, so this feature is the fact that you can violate these classical expectations is really something that is intrinsic to quantum mechanics, and really it appears for these quantum entangled states. Okay, so the same kind of character, same property we'd like to apply to understanding many body systems. Okay, so to sort of giving some insight into many body systems, we need a simple measure of this quantum entanglement, and that's given by this entanglement entropy. So what you do is you have a system which is in a pure state, you trace out some degrees of freedom, and then you just get something that is relevant to the remaining degrees of freedom. Let's call that the system A. You end up with a density matrix for system A, and then you can define an entropy, the typical probability times log of probability kind of function, and this gives you an entanglement entropy. Okay, so you can do this on this fixed state of ours, 0, 0 plus 1, 1, and if you trace out one of these spins, let's say you trace out the second one over here, you're left with some density matrix for just the first qubit, and it's got a 50-50 chance of being in 1 or 0. Okay, so the entanglement entropy is just log of 2. Okay, so so you can generalize this to a many-body system, and the entropy in this case, we're going to think about some extended system like this. Everything that's inside this red region is going to be retained. You end up getting some entanglement entropy for that region. And you can ask, how does that entropy change as you change the size of the system? Okay, and the interesting observation that seems to be quite general is for many states, this entanglement entropy changes only very slowly. Okay, if you look at ground states. Okay, and in particular, although the number of particles you have grows with the area of this system, this entanglement entropy only grows with the perimeter. It's just proportional to the boundary of the system. Okay, so you can write it in this form. This entanglement entropy is just proportional to the perimeter, the linear size of this A. And it may have a constant term. And it turns out all of the physics that we are interested in is sitting in this subleading constant term. Okay, so to cut a long story short, if you ask what is the distinction between the integer quantum Hall effect and this fractional quantum Hall effect, really a sharp distinction. One very good way of doing it is to say that this constant is going to be 0 for the integer quantum Hall-like states, and it's going to be some fixed number for the fractional states. And that distinction allows you to classify, for example, all of the states that are like the integer quantum Hall effect. Okay, so for a long time we were missing this kind of definition. People were using distinctions like, this is a non-interacting state and this has interactions. But once you adopt this particular way of thinking about the distinction, you could actually get interacting versions of the integer quantum Hall effect. States that are sort of like the integer quantum Hall effect, only present if you have strong interactions. Okay, and so ultimately what has emerged from this is, the program was to classify all the gapped, all the states of quantum matter. The gapped states are the easier ones to classify. So now we have made a lot of progress, classifying all states of matter that are like the integer quantum Hall effect. We call them short-range entangled quantum phases. Part of that is the free fermion states, like these topological insulators and integer quantum Hall states. They're classified by a mathematical theory called K-theory. But once you have interactions, it turns out the classification is different. Still working on this, but I think to a large extent we understand this physics pretty well. And what people have now turned to is to understand the states that are so-called long-range entangled phases. So things like the fractional quantum Hall states. It's pretty well understood in 2 dimensions. Again, at least mathematically, we understand it pretty well. But it turns out in 3 dimensions, in 3+1 dimensions, there are a lot of exotic-looking states. They don't have conventional field theory descriptions. There are these so-called fracton states, which only propagate in some reduced dimensional space. There's a lot of complexity in 3 dimensions, and that's really where a lot of people who are interested in the more formal aspects of this classification are. Okay, but a lot of this classification happened over the last decade, I would say. So there's been enormous progress from knowing a few examples to really being able to say we kind of know them all, okay, at least for these gapped quantum states. Okay, now, of course, you might say that gapped states of matter are very simple. If you look at low energies, there's actually nothing happening, right? Once you go below the energy gap, there's really no dynamics. Nothing is moving around. It's all very simple. And all of the action, if there is any action, happens at the edges. Okay, so you may say this is going to be of very limited use to understanding things like metals or things that have a lot of low energy physics present. But surprisingly, that's not been the case. So we've actually used these insights to understand also gapless states. And the way the connection works is, these gapless states occur at the boundaries of these gap phases. And often they constrain them very strongly. So recently, one of the applications I'll quickly mention is we've been able to find new dualities by understanding these topological phases better. And with these dualities, we have also understood some of these quantum Hall states that are actually gapless. We've had some things to say about them, at least some sort of universal features that have to be true because of these connections that were discovered. Okay, so let me try to give you a flavor for this. It's, of course, the details are rather technical, but hopefully I'll be able to give you some qualitative kind of picture what was done over here. So so the starting point is this so-called 3-dimensional topological insulator, which is gapped in the bulk, but it has these gapless excitations on the boundary, which look like Dirac fermions. Okay, well, the interesting thing is it's just a single Dirac fermion, and in 2 dimensions, you're not allowed to get that if you have time reversal symmetry, okay, or reflection symmetry. There's a parity anomaly, but you always have to break that symmetry to define a single Dirac fermion. Okay, but by going to 3 dimensions, you can get the single one. These are called the topological insulators. And this is a perfectly good description in terms of non-interacting electrons. But if you want to talk about the strongly interacting regime, that's not the right variable to use often. If the particles are interacting very strongly, it's very hard to see what can happen. You'd like to come up with a different description of the same problem, a different set of variables, which is more suited to strong interactions. You'd like to map, in a different set of variables, the strong interactions could become weak and vice versa. Okay, so these kind of mappings are called dualities. And it turns out the relevant one to think about here is the so-called electric magnetic duality. Okay, so if you just look at Maxwell's equations in 3 dimensions, in the absence of any charges. Okay, so divergence of E and B are 0. There's like a symmetry between them. Okay, you can imagine switching the electric and magnetic fields around. The equations will look exactly the same. Okay, so there's a different description of electrodynamics where you kind of switch the roles of the electric and magnetic fields. Okay, so what's interesting about this different description is that you can now insert charges. Okay, so if you had electric charge and magnetic charges, that's magnetic monopoles, you of course find this consistency condition discovered by Dirac that if you have a certain magnetic charge, the electric charge cannot be anything you like. It has to be 2 pi divided by this magnetic charge, okay, to ensure consistency of the quantum mechanical wave functions. Okay, so there's this nice connection between the electric charge and the magnetic charge, and you discover that if you have Coulomb interaction between electric charges and you compare that to the interaction between the magnetic charges, these have an inverse relationship. Okay, if this electric charge is very big, there's strong Coulomb interaction between the charges. The magnetic charge is going to be small. The magnetic particles are going to be weakly interacting. Okay, so that's the clue that maybe if you want to talk about strongly interacting topological insulators, you should talk in terms of not the particles, but the magnetic monopoles, and the magnetic monopoles will be weakly coupled. Okay, so I've skipped a couple of steps. We actually gauge the topological insulator. You sort of expand the excitations by allowing for these monopoles. Eventually, you're going to get rid of those monopoles. Okay, it's sort of a theoretical kind of trick. But the basic idea is this, that the strong interaction between charges can be described more easily as weak interactions between monopoles. Okay, and so if you look at the set of excitations in your problem, you have things which have electric charge, you have things that have magnetic charge. Okay, and so this is the electron, one electric charge. It's colored red because it's a fermion. This is the magnetic monopole. It's colored blue because it's a boson. Okay, and this is the state of affairs usually. If you take this and put it inside a topological insulator, there's a very interesting effect called the Witten effect. Okay, so what Witten showed is that if you have a certain theta angle, the theta angle is pi for this topological insulator, now the magnetic monopoles begin to get charge. Okay, they attract charge, and the charge is really the half the magnetic monopole charge. Okay, so on this, graphically what happens is that these things move. You end up getting charge on the magnetic monopoles, and then you find that conveniently there's now a magnetic monopole which is a fermion. It's actually a doubled magnetic monopole. Okay, so it turns out instead of talking about topological insulator in terms of electrons, you can talk about topological insulator in terms of this monopole. And that gives you a weakly coupled theory of the magnetic monopoles. So this is the topological insulator in terms of electrons. It has the surface state. This is topological insulator in terms of monopoles. You can show that it remains a topological insulator, and it also has a surface state of these monopoles running around. Okay, now you can play a lot of games with this. You can say, what if I apply an electric field on this side? Okay, if you apply an electric field, it turns out you charge up the surface. You get some particles on the surface. But what happens on this side, so the duality is the electric field goes to magnetic field. You end up putting a magnetic field on a Dirac fermion. You get Landau levels. And this Landau level is always half-filled because it's magnetic field on a Dirac fermion. Okay, so it gives you a connection between a physics of a problem with the half-filled Landau level and a different problem where fermions are at some finite density. Okay, and it also tells you these fermions are actually have a Dirac kind of character. Okay, so this sort of gives you insight into this half-filled Landau level. It's to some theory of interacting Dirac fermions, and it turns out this has consequences. Okay, so we could see some of the consequences in numerical calculations. There's a scattering event that's forbidden on the surface of topological insulators because they have opposite spin, and when we calculate numerically the similar physics for the half-filled Landau level, you clearly see this is absent. And it would be a mystery if you didn't know about this mapping between half-filled Landau level and this Dirac fermion. Okay, there's another more interesting connection. So it turns out you can take these fermions and make them into a superconductor. You can just pair the fermions. There's a very obvious kind of pairing mechanism you can have over here. Just pair things on opposite sides with the same strength. That actually turns out to give you a particular quantum Hall state. Okay, it's called the pH Pfaffian or the T Pfaffian, depending on who you follow. So Sohn called it the pH Pfaffian. And in principle, it could be a candidate state for this 5 halves that I talked about before. Okay, so depending on different pairing mechanisms you have for this Fermi surface, you get different candidates over here. So no one actually had thought about this particular candidate, or somehow not considered elegant or something. They had other candidates corresponding to different pairing functions, but there's a recent experiment which is most easily interpreted in terms of this particular state. Okay, so this development, people started thinking about the state because of this duality physics, and now there's an experiment that seems to be consistent with this particular state. We still have to wait and see if there's some problem with the experiment. Nobody has repeated this. It's an extremely hard experiment. It's called the thermal Hall effect, but it would be very interesting if this thing holds up.
I'm really sorry, I should know this better, but the original duality where you had these boundary states of topological insulators, when you went to the magnetic monopole picture, half your Landau level was it weakly coupled in that description there?
Yes, yeah, you could do either, but let's say it's weakly coupled. So let's say, actually, you know what, I want that side to be strongly coupled. If I put the magnetic field on that side, so let's say I have the half-L Landau level with strongly interacting particles. There's a duality to fermions that are weakly coupled with the Fermi surface. And then you can describe that.
Then that side becomes useful.
Yeah, that's right, yeah. But you can play it the other way around as well if you want. Yeah, that's a good question. It's almost the same. So there's a slight twist which is different. So there are 3 phases, it turns out. And one is called the Pfaffian. And there's an anti-Pfaffian. So this is, if you think in terms of topological order, it's something like Ising times, there's something for the charge part. This thing is not very important. You can think of this as, yeah, I'll come back to this in a second. So previously, people thought it's either this or that, one of these 2 things. And they didn't know which of these 2 because these are related by particle-hole symmetry. So if you have particle-hole symmetry on the Pfaffian, it becomes the anti-Pfaffian and vice versa. And the breaking of particle-hole symmetry in the Landau level is very weak. So people had to really work very hard to know which of these 2 was better in numerical calculations. So one way out was this so-called, which is close to itself under particle-hole symmetry. That's what the pH is. And in terms of superconductivity, you can take this problem of the half-L Landau level and think of it in terms of fermions that do not experience a magnetic field. And then all of the superconductors of those fermions, this Pfaffian and anti-Pfaffian correspond to doing something like a D-wave superconductor on this. So D plus ID or D minus ID. And time reversal symmetry is the analog of particle hole. You get them to be conjugate to one another. But the most obvious kind of superconductivity you would have is just S-wave. And that turns out to be this pH Pfaffian. So from this Dirac point of view, it's very natural to get the pH Pfaffian. It's a bit of a mystery why you would get one of these. But numerically, you seem to get this, at least in numerical calculations on small systems. But experimentally, you seem to prefer this. So there's a bit of a, in quantum Hall, the numerics usually works very well. So maybe it's something like disorder, that we had a theory that maybe disorder gives you puzzles of this and that, and taken together, they can kind of look like the state. But it's still a bit of an open question, how to reconcile all these facts. But they're very close to each other. They all have the same kind of non-abelianness, which is this Ising. It's just how the Ising is connected to the charge degrees of freedom that's different. Okay, how much time do I have, Shaz? Are we almost out of time?
About 13 minutes.
13 minutes, okay. That's all I need.
Just one last thing.
Yeah, sure.
Is that a semi-direct product? Is that the point? The Z2
there is something like that. Yeah, there is some mod. There are fermions in this theory. theory of electrons. So that makes it a very strange topological theory. So usually in a topological phase, if you have a particle that has no mutual statistics with anything else, it's trivial. You don't put it in the theory. But here you have electrons. So electrons have no mutual statistics, but they're there in the theory. They're fermions. You cannot just condense them. So because of that, all of these are, mod some kind of Z2. I don't know what the correct notation is, but it corresponds to condensing this, the product of that fermion and the electron. Yeah, so let me tell you another application, or at least some of these ideas that came up again in a very unusual context, which is there's this amazing experiment on these graphene superlattices, which I'll describe in a little bit. And this is work with these collaborators of mine, especially my student, actually his former student, he's moving now for a postdoc at MIT, Adrian. So what we had over here, what was done over here was people took graphene, which is just a layer of carbon atoms. They took 2 sheets of graphene, but not perfectly aligned. Okay, they were slightly misaligned. They were rotated by a very particular angle. So theoretically, it was predicted that if this angle is something called a magic angle, which is about 1 degree, you would get a very kind of flat band, kind of like quantum Hall physics, where there's very little kinetic energy, and the interactions would be very important. People didn't know what would happen. They just said, oh, the interactions are going to be very important, maybe interesting to try. So people tried this. So this is again a classic condensed matter question. You take 2 sheets of graphene, rotate them by 1 degree, what happens? Why would you do that, right? But anyway, so they did that, and they found this amazing result that this is, so if you remember, graphene has got these Dirac points. The electronic structure of graphene, maybe I need a slide on that. It looks like that. Okay, so at low energies, the physics of this graphene looks like Dirac theory, and that's why we end up getting all kinds of topological things when you begin with graphene. Okay, so here also you have this, but you have 2 layers, so you have 2 copies of this, and you put them on top of each other and rotate them a little bit. Okay, and what they found is that they can measure the conductance as a function of how many electrons they put into this system. And what they found is there are certain band gaps, which I'll explain in a second. There are band gaps, very conventional stuff coming from this, this superposition. But there are also these very interesting states that they get where the number of electrons, where you're sort of at half filling, and you get something called a Mott insulator that's produced because of interactions. And if you dope that Mott insulator, if you go a little bit away in density, you end up getting a superconductor. Okay, so the maximum TC they get, I think now it's gone up above 2 Kelvin, simply by taking this pair of graphene sheets and twisting them a little bit and putting them on top of each other. Okay, so the origin of this physics is if you just look at a picture, you take a pair of these things and twist them a little bit, you see a pattern that looks something like this. Okay, you see that just from the naked eye, you can kind of tell that there's some bigger lattice that's been formed over here, right? And the length scale of this lattice is essentially 1 over the angle, the original scale divided by the angle. So if you have an angle of 1 degree, 1/60th of a radian, these scales are 60 times bigger than the atomic scales. Okay, and when you do this and solve for the band structure, you end up getting these isolated bands that live near the near the neutrality point. Okay, this is where the chemical potential of graphene was before, and all of the action is taking place inside these bands. Okay, so this is something that people are trying to understand. How do you get, if you take these bands, if you look at how big the band width is, this is a measure of the kinetic energy, it turns out that the interactions are comparable or even larger than this bandwidth. Okay, so this is really a regime where the interaction physics is dominant, and you can get all kinds of interesting things, which is basically what people saw. Okay, so just to give you a sense of where this magic angle comes from, why is this angle 1 degree special? So if you take a pair of these graphene dispersions and superimpose them, separated by a small angle, you see that there is a splitting over here. There's an energy gap over here. And this is controlled by basically the velocity of graphene times this angle, right? So the scale over here is the wider the angle, the more you separate out these Dirac points, and the larger that gap gets. And the closer you bring them, the smaller it gets. To allow for some coupling between these layers, you have to allow for electrons to tunnel between them. And if you want some effect, you need that tunneling to be of the same order as the splitting over here. And that's what, and you know, there's some microscopic value for that tunneling. It's some number, and that allows you to set this angle, which turns out to be about 1 degree. That's the first, the first magic angle. Okay, so what is the connection to the topology talking about before? So if you look carefully at this band structure, you know, it again has these Dirac points. And you can actually define something called a chirality for these Dirac points. Okay, how the you know, how these Pauli matrices rotate as you go around these Dirac points. And what you find is that both have the same chirality. Okay, in some sense, it's like one of these surface states. If you just look at this particular band, it's like one of these surface states. And that actually makes it hard to write down a simple model to capture this physics. You cannot simply write down some tight binding model of fermions hopping on this bigger background, which ends up giving you this exact same band structure. Okay, so this is something we have been working on, how to actually capture the band structure of this material in some nice model. But there is this important fact that, you know, this the topology of these K and of these bands, you know, end up constraining the physics of the system in some interesting way. We're still trying to figure out if it's key to getting the superconductivity or it's kind of a sideshow. But so far, just to write down a correct model for these the bands where all the action is taking place has been more challenging than it's been in some of the other contexts. Okay, so for example, in the cuprates, very similar kind of physics happens. You get a Mott insulator, you dope it, you get a superconductor. But it's quite easy to write down what seems like a microscopic model for the cuprates. It's just a square lattice Hubbard model. We want the analog of that square lattice Hubbard model for this problem, and it turns out it's not as easy as it you know, as it may appear. Okay, and the reason really is that there is some interesting topology in these bands that you need to capture. Okay, so maybe this is a good place to stop. I tried to tell you about you know, some of the you know, a lot of concepts in these in the physics of many-body quantum systems that's really been crystallized over the last maybe 1 decade. It's brought together a lot of things that we thought of as different. And you know, the key ingredients that went in were really this understanding quantum entanglement better and understanding topology of these quantum mechanical systems better. And we saw a few applications of this physics, you know, to sort of topical problems. There's this quote that you know, this many of you may know this person, especially in India. A lot of people, I think he designed the city of Chandigarh, right? But he has this very kind of optimistic quote that today's reality is yesterday's, you know, dream or utopia, right? And today's dream is just going to be the reality of tomorrow. So he was definitely not talking about politics, I'm sure. He was probably talking about exotic quantum phases. Right? Yeah, so anyway, maybe let me end there.
Okay, we'll have questions, but before that, let me just say that Ashvin is going to give more detailed technical talks from 11 to 1 tomorrow and the day after. Tomorrow's talk will be here, so 11 o'clock tomorrow. Okay, so questions.
Okay, so Ashwin, you mentioned how the understanding of the gap phases can lead one to also understand something about gapless phases, say on the boundaries and so on.
Right.
Now, one very, of course, interesting and important gapless phase is just when you get Fermi surface.
Mm-hmm.
That too has a characteristic signature, as you well know, in entanglement.
Mm-hmm.
And I was just wondering whether that story has been developed further to classify, I mean, are there phases similar to those with Fermi surfaces or different types where you see signatures and that?
Yeah, so actually one of the examples I gave has that flavor. So that was the this Dirac, this kind of Sohn's theory for the half-filled lambda level. So people knew before that there's a way to think about the half-filled lambda level in terms of different variables, composite fermions due to Jen, and people as a Fermi surface of these composite fermions. But what turns out to be the case is that if you take particle-hole symmetry seriously, then this Fermi surface is actually this Fermi surface of a Dirac fermion. So if I go around the Fermi surface, I acquire a Bery's phase. So the distinction from the previous theory is in that aspect, but that aspect is topological, whether it's Dirac-like or not Dirac-like, just a regular Fermi surface. And that's sort of a manifestation of a quantum anomaly. So this quantum anomaly can be hidden inside a Fermi surface as well. And it has some, the effects are subtle. It's not obvious that it's Dirac-like. That's been a challenge. How do you tell it's Dirac versus what is called HLR, Halperin-Leary, the earlier theory, which was based on composite fermions of the regular variety. The distinction is subtle, but this is one of the smoking gun signatures. That this is like the surface of a topological insulator where the spin rotates around. You cannot get a scattering of this electron there because they have opposite spin. So we do this numerically for this half-filled lambda level, and we see the missing wave vectors. The most obvious wave vector is missing, which is the one that goes from one side to the other.
I think your topological aspect did not come out in the twisted layer explanation that you gave.
Yeah.
Twisted by layer.
Yeah, I can make that a little more precise. So here's the deal, right? You have this twisted bilayer. You have some mini band, like it looks like that. There are some bands above and below. So all the action is taking place in this mini band. If you count how many bands you have, it looks like the same as graphene. Right? So you have this moire lattice, and so that you can draw some sort of honeycomb lattice there. Actually, there's some honeycomb lattice that you can draw. And you can say, oh, maybe I can just consider this honeycomb lattice on this moire scale, write on a tight binding model over here, and I can get this band structure. You would like to do that. That's like the starting point. Then you can add some Coulomb interaction and stuff like that. Turns out that it's impossible to do that. You can never write down tight binding model on this honeycomb lattice, which will reproduce this band structure. And the formal way of saying it is because there is the chirality of these two Dirac points are the same, whereas any tight binding model will give you an opposite chirality. But a more physical way of saying it is that if you had a tight binding band structure like this, let's say you did it, you came up with something, then what I could do is I could add a small potential like this, or opposite potential on the A and B sides. It'll give a gap. But because of this chirality, this gap band structure will actually have, it'll have Chern number 1, this will be Chern number -1. But then, this is inconsistent because I can increase the potential and eventually the electron will just be trapped over here. But that means I have a way to make a Chern band where the electrons are localized on sites. That's not allowed. It won't have surface states and stuff like that. So here, everything is kind of flipped around from the usual case. Usual case, if I give you graphene band structure, I need to do this hopping to get quantum Hall. Here, just the staggered potential gives me quantum Hall. And this Haldane hopping gives me what staggered potential gave for the graphene. So it's kind of flipped the Haldane model, and that is a topological aspect. So in order to get a model like this, you have to give up something. Either you take, so this was like for one valley, I didn't talk about that. You have to either do both valleys, or another thing we can do is we can add some bands to it. And then you can have something like a PD model, what people call PD model for cuprates. So you add some additional bands, and then the whole thing you can describe by a tight binding model. But there's some obstruction there, which is why we call it something topological.